In this video, you're going to learn what graph autoencoders are, how they work, and why they are useful. Graphs appear everywhere, from social networks to transportation systems, and they capture how things are connected. But working with graphs directly can be complex. So the key question is, can we compress this structure into something simpler without losing the important information? That's exactly what graph autoencoders do. Now let's take a closer look at how this works. We start with a graph. A graph is a set of nodes connected by edges, representing relationships between different entities. Our goal is to transform this graph into a simpler representation, while still keeping its structure. First, the graph is passed through an encoder. The encoder takes each node and maps it to a vector. This vector is a compact numerical representation of the node and its connections. These vectors form what we call a latent space, a compressed version of the graph. In this space, nodes that are similar or strongly connected end up close to each other. Even though this representation is much smaller, it still preserves the important relationships in the graph. Next, a decoder uses these embeddings to reconstruct the graph. It predicts which nodes should be connected based on their representations. If the reconstruction is accurate, it means the model has learned the structure of the graph. Now we'll take a closer look at each part of the algorithm, the encoder and the decoder, in more detail. Let's start with the encoder. We begin with a graph of 4 nodes. From this graph, we first build the adjacency matrix A. Each row tells us which other nodes a given node is connected to. For example, if 2 nodes share an edge, the corresponding entry in the matrix is 1. Otherwise, it is 0. Next, we add self-loops. This means that each node also takes its own information into account. So instead of only looking at its neighbors, each node also keeps a connection to itself. This gives us the modified adjacency matrix. From there, we compute the degree matrix D. This matrix stores on its diagonal how many connections each node has after adding self-loops. Using these 2 matrices, we can now compute the normalized adjacency matrix. This normalization is important because it keeps the aggregation stable and prevents highly connected nodes from dominating the result. Now we combine this normalized graph structure with the node feature matrix H. Here, each row of H represents the features of one node. A feature is simply a numerical description of a node. For example, in a social network, a node could represent a person, and features might include age, number of friends, or interests encoded as numbers. In a molecule graph, a node represents an atom, and features could describe the atom type, such as carbon or oxygen, its charge, or other chemical properties. In general, features are vectors that capture the properties of each node in a way the model can process. So for every node in the graph, we have a corresponding feature vector, and stacking these vectors together gives us the matrix H. The full GCN update is then given by Z equals H of 1 equals sigma of A hat times H times W. Here, W is a learnable weight matrix. It transforms the aggregated features into a new feature space. You can think of it as similar to the weight matrix in a standard neural network layer. After each node has gathered information from its neighbors through A hat times H, the matrix W is applied to learn which combinations of features are important. For example, it can learn to emphasize certain attributes while suppressing others. During training, W is optimized so that the resulting embeddings are useful for the task, such as classification or reconstruction. In other words, each node aggregates information from its neighbors, and this aggregated information is then transformed by learnable weights. The output is the matrix Z. In our example, the output dimension is 1, so the weight matrix maps each node's features to a single value, resulting in a 4x1 vector Z. Each row of Z is now a learned latent representation of one node. So at this point, the graph is no longer represented only by edges and raw features. Instead, it is represented through learned embeddings. To build intuition for this latent space, we can visualize these embeddings geometrically. The vector shown here represents the latent direction associated with the embedding matrix Z. Since the learned embeddings live in a higher dimensional space, we project them down to 2 dimensions for visualization purposes. This is a simplification that allows us to illustrate the structure of the latent space. Now let's consider a second graph that is very similar, except that one node has changed.
If we pass this graph through the same encoder, we obtain a second embedding matrix, Z prime. Its latent vector points in a similar direction. And that is exactly what we want. Similar graphs should lead to similar latent representations. So the encoder maps graph structure into a latent space in which similarity in the original graphs is reflected by similarity in the learned representations. In the next step, we will see how the decoder uses this latent representation to reconstruct the graph.
Now, let's take a closer look at the decoder. The goal of the decoder is to reconstruct the graph structure from the latent representation Z. To do this, we compute the similarity between all pairs of node embeddings. Concretely, we multiply Z with its transpose. This produces a matrix where each entry reflects how similar two nodes are in the embedding space. We then apply a sigmoid function to map these values into the range between 0 and 1. The result is the reconstructed adjacency matrix. Each value now represents the probability that two nodes are connected. Next, we compare this reconstructed matrix with the true adjacency matrix of the graph. This comparison is done using a loss function. The loss measures how different the predicted connections are from the actual ones. If the model assigns a high probability to a non-existing edge, it is penalized. If it assigns a low probability to an existing edge, it is also penalized. The objective is to minimize this difference. Because all operations are differentiable, we can use backpropagation. The error signal flows from the loss through the reconstruction step back into the embeddings and further into the encoder. This allows the model to adjust its parameters so that the reconstructed graph becomes more accurate over time. In this way, the model learns representations that capture the underlying structure of the graph.
Let's now step back and look at the big picture. A graph autoencoder consists of two main parts, an encoder and a decoder. The encoder takes the graph as input and transforms it into a latent representation. This representation is a set of vectors that capture the structure and relationships within the graph. The decoder then takes these embeddings and tries to reconstruct the original graph. It does this by estimating which nodes should be connected based on their similarity in the latent space. To measure how well the reconstruction matches the original graph, we compute a loss. This loss compares the true adjacency matrix with the reconstructed one. If the difference is small, the model has successfully captured the structure of the graph. If the difference is large, the model needs to improve. This is where backpropagation comes in. The error is propagated back through the decoder and the encoder, adjusting the model parameters so that future reconstructions become more accurate. Over time, the encoder learns to produce embeddings that are highly informative, and the decoder becomes better at reconstructing the graph from them. In this way, the model learns a compact representation of the graph while preserving its essential structure. This is the core idea behind graph autoencoders. Let's now look at some important limitations of standard graph autoencoders. First, the embeddings are deterministic. Each node is mapped to a single fixed vector, which means the model does not capture uncertainty in the representation. Second, there is no strong probabilistic interpretation. The model reconstructs the graph, but it does not learn a full distribution over possible embeddings. Third, this can lead to overfitting. Since the embeddings are learned directly from the data, the model may adapt too closely to a specific graph and struggle to generalize. Finally, the latent space is not explicitly structured. While it may work well for reconstruction, it is not enforced to be smooth, continuous, or well-organized. These limitations motivate a more principled approach. Variational graph autoencoders extend this idea by learning a distribution instead of fixed embeddings. This leads to a more robust, interpretable, and better structured latent space.
Let's summarize the key ideas. Graph autoencoders learn embeddings by reconstructing graph structure. The encoder maps nodes into a latent space, and the decoder uses these embeddings to recover the connections. This allows us to represent complex graphs in a compact and meaningful way. However, standard graph autoencoders are deterministic, which leads to important limitations. This motivates more advanced approaches. In the next video, we will look at variational graph autoencoders, which introduce probabilistic latent representations. Thanks for watching.